In the end of last lecture, we started to discuss muon decay, and what has been observed is that new particle discovered in 1936 has a decay into electrons and 2 neutrinos, and this is needed to explain the continuous spectrum of electrons observed from this decay. Very similar to what we had in the case of beta decay. So we constructed the Hamiltonian, which describes such a decay to a large extent in analogy now with beta decay. The Hamiltonian has the form of product of two currents. One current is electron, neutrino and electron, and this pair is exactly similar to what we have in beta decay. And instead of proton and neutron, we have transition of muon into another neutrino, and this is described by this new current, which contains muon and muon neutrino. So this is product of two currents, and it was some question. Let me underline that this is the way to construct Lorentz invariance. That's Lorentz invariance again. Because all these fields are fermions, and therefore to construct Lorentz invariance combination, so which means that they are proportional to Dirac spin-offs, and to have a Lorentz invariant combination, we need to connect two spin-offs, or bispin-offs. One is conjugated, Dirac conjugate, and another one without conjugation. We also introduce gamma mu, and gamma mu here, and there's a connection mu here and mu here. So all this ensures that the Lagrangian is Lorentz invariant. I have written here the form the same as we had for beta decay of the currents, which are V minus A. It contains gamma mu minus gamma mu gamma phi. So we will discuss this in details later when we will discuss discovery of bidetic violation. Let me introduce in more details a notion of rates of decay. Rate of decay, usually called gamma, is the probability of decay in the unit of time. So if we have the system of particles, and in initial moment t equals 0, there are n0 particles, then the change of number of particles due to decay is described by question dn dt equals minus gamma n. So minus sign shows that there is a decrease of particle, and decrease of particle is proportional to the rate of decay multiplied by the number of particles with this initial condition. The integration is trivial, which gives dn over dt equals minus gamma, sorry, yes, n divided by n, gamma dt. And therefore integration gives n equals n0 exponent minus gamma t. And for t equals 0, we reproduce exactly n0. So the number of particles decreases exponentially, and gamma gives us the rate of this decay. Apart decay rate, we also introduce lifetime, which is inverse of gamma. So this is lifetime of particle. So this is general, not only for muon decay, which we are discussing, but it is general. So we have this exponential decrease, number of particles, the function of time, and here we have exponential decrease of number of particles. Gamma is inversely proportional to lifetime, and really it has dimension of mass. This is dimension of decay rate. Let us compute decay rate for muon decay. Again, I will use dimensional arguments to find this decay rate. The important physical conditions are the following. First, the mass of muon is much bigger than the mass of electron, and this is much bigger than the mass of neutrino. Remember, the mass of muon was around 100 MeVs. Mass of electron is 0.5 MeVs, and neutrinos are much, much lighter. So that in the first approximation, we can consider electron and neutrino as a massless. And the only parameter of the dimension energy is m muon. Second, as I said, the dimension of gamma is the mass. Let me put it again. And finally, we can look at the Hamiltonian. So what we are doing usually when we're computing probabilities of cross-sections, we first compute matrix element and then compute moduli square of the matrix element. So here we have in final state neutrino, and electron, the Hamiltonian, and in initial state muon, and therefore the rate is proportional to square of this matrix element. Now we introduced G mu in analogy with G beta decay or G Fermi, and this can be done again on the dimensional ground, and clearly that the gamma should be proportional to G mu squared. Now, dimensions are the following. This is mass. This is 1 over the mass to the 4th power. We did this counting for beta decay. And therefore, to satisfy dimensions, we need to write the mass to the 5th power. Right? And since the only parameter here of the dimension mass, the most important is the mass of the muon, we get here mass of the muon to the 5th power. Now, exact expression for beta decay rate is in the lowest order. G mu square multiplied by the mass of the mu to the 5th power. And now 192, big coefficient in denominator, pi cube. This is the lowest order. And of course, if you do not neglect masses of electron and muon, you will get some corrections like 1 plus mass of the electron over the mass of the muon. Something like this, which you can neglect. So at least with accuracy better than 0.5%, you can use just this expression. Of course, there are also radiative corrections, which we are not discussing here. Now, this big coefficient comes from the fact that in the final state, we have 3 particles. So muon, electron, neutrino, and neutrino. And when we compute the probabilities of the processes, we are doing integration over momenta of these final particles. I've already told you once. So this is total rate. If you want to compute the rate of decay when electron in final state has some specific value, then we shouldn't make integration over all the momenta of these particles and keep one of these momenta fixed. So, however, if you are interested in the total rate, we need to make integration over all these variables. This means that we have integral like d p electron 2 pi cube and the same dp neutrino 2 pi cube. This is what we call the space volume. dp another neutrino, electron is another neutrino, 2 pi square, cube, sorry, 2 pi cube. Well, from this you can also see the following. When we are doing integration, we are doing integration from 0 to maximal area of these momenta. And in the case of 3 particles in final state, we may have the situation when, for instance, electron has close to 0 momentum. And we may have the situation when all the momentum of muon is taken by electrons. So actually we do this integration from essentially 0 to the maximum possible momentum, and maximal possible momenta are determined by the mass of muon. And for this reason, this integration precisely gives us this big power of mu. But technically, when we are doing computations, and you will learn how to do this in electrodynamics, you can repeat it here. So this big power comes from integration of the phase volume. Also, this big coefficient comes from these 2 pi cube, mainly. And for instance, in contrast to two-body decay, where we have just 1 pi in denominator, here we have additional factor 2 pi cube. But when we do our angular integration, so we have in denominator 2 pi when we do integration over azimuthal angle. And we are getting precisely that in contrast to two-body decay, we have additional 2 pi square parameter. And so instead of pi, we have pi to the 3rd power. Okay? Let me delete this explanation, but you see we got this answer essentially using dimension arguments. And let me repeat again, even this power can be found without any computation. It's just knowing how many particles in final state and what you are doing, how you integrate this. Now, the important property of this result is that the rate is proportional to the 5th power of the energy release. Actually, the same situation occurs in the case of heat decay. In that time, in the case of liquid decay, Q is difference of masses of initial and final nuclei. Here is the difference of mass of muon and electron. And if you neglect mass of the electron, then Q is just mass of the muon. So this is important property of so-called three-body decays when you have in final state three particles like here. So in this case, unless there are some specific reasons, you get this answer. Let me say you the following. When we are discussing physics, we are not coming every time, to our desks and to make complete computations. When we are discussing physics in the first place, we are trying to do estimations and to get kind of idea what's going on without lengthy computations. Then, when we convince ourselves that computations should be done, then we are going into making computations. So therefore, knowledge of this type of properties is important. That will make your life easy and more efficient in doing the things. Now, from the experiment, it has been found that tau is 10 to the minus 6 seconds. Actually, this is the lifetime of muon, which is worthwhile to remember. Because knowing this, you can reconstruct or find out other things easily. So, since you know gamma, or this expression for gamma, and lifetime is 1 over gamma, the only unknown in this formula is G mu. Therefore, knowing the lifetime of muon, you can find what is G mu. So, this from lifetime, measured lifetime, what has been found, and this is extremely important result, which is on the basis of the standard model, is that this G mu is essentially coincides with G thermal. So, what emerges from this is universality of weak interactions. Without this, you would not construct the standard model. Discovery of muon was to some extent unexpected discovery. Because, what's surrounding us are atoms, nuclei, and this is made out of electrons, protons, and neutrons. So to create our world, it is not necessarily to have muon. Now, why nature created this additional particle? And that was famous question by Rabi, who was asking who ordered existence of muon. Discovery of muon created was the first sign of the so-called flavor problem. So now we have electron and something which is very similar, which is muon, which has practically the same properties apart from the mass. And as a consequence of mass, muon decay in contrast to electron. So the question is why this second charged lepton exists, and then we will discuss that the third one was discovered. So why do they exist and why the masses are so different? So this is the question of so-called flavor physics and flavor problem, which we still have no answer to. Another important point is with measuring of this lifetime is that muon is not Yukawa particle. About the time of discovery of muon, Yukawa produced the first theory of strong interactions. The interactions which describe nuclear structure and the interactions between protons and neutrons inside the nuclei, and he introduced new particle, which is Yukawa particle, and that particle exchanged by this particle mediate this strong interaction. So it has very strong coupling with protons and neutrons. So it has protons and neutrons, and protons and protons. And Yukawa introduced scalar particle. Now we know this as a pion. And he estimated also what should be the mass of this particle. It's easy to estimate because you know what is the size of the nuclei. And to keep this system, you need to have mediator mass which is inverse of the size of the nuclei. If you remember these discussions about the sizes of dimension of objects and the masses, and therefore it was estimated the mass of the pion should be inverse of 10 to the minus 13 centimeters, and you will get that the mass of the pion should be around 100 MeVs. And the fact that muon has been discovered, first people thought that, oh, this is Yukawa particle. However, Yukawa also predicted what is lifetime of this particle. And it was at least 2 orders of magnitude bigger than this quantity. So the measurements of lifetime of muon also allowed us to make conclusion that muon is not Yukawa particle. Questions?
I have a question. So when we say muon decay into electron and to neutrino, so are we here like specifically indicating like it is electron neutrino, or?
By the time when this decay has been observed, people didn't even thought that it may be several different types of neutrinos. They didn't specify, so that just 2 neutrinos should be emitted. And it is later was shown that one of the neutrinos in association with muon differs from neutrino which is associated with electron. So I have written here the Hamiltonian as we know now. So here I put index mu, and here I put index E, indicating that actually 2 different neutrinos are in these currents. But by the time of discovery of muon, that was not known.
Thank you.
More questions? Okay. So now we move to discovery of pion, Yukawa particle. So let me again stress that this measurements and discovery of muon allowed us to introduce the concept of universality of weak interactions, essentially. Which means that we have weak interactions, like beta decay, muon decay, which have the same structure as product of currents and product of this B minus A currents with the same coupling constant. Okay. Now discovery of pion. which also allows to introduce many concepts. You see, there are very important particles, many particles, thousands of particles, but some of them are extremely important because studies of their properties allowed us to develop the theory, all the theories. So we do not need to study properties of all these particles, which we know now, to write standard model Lagrangians. So the Lagrangian was written on studies of properties, just a few particles. What is important, that after construction of the total Hamiltonian Lagrangian of the theory, we can make some predictions and describe properties of many other particles. So this is whole idea. This is why we trust that what we constructed is really a correct thing. So you actually need to anytime ask question. So we have written this Hamiltonian and correct question, is this correct theory or can we produce some alternative theory? It's always important to ask this question and then convince yourself why some other possibilities are excluded. Coming to discovery of fine, it was kind of a story, a history of this discovery, which is actually of the history of strong interactions. Which were introduced as interactions which ensure the existence of nuclei, that is strong forces between protons and neutrons, and even between protons and protons, which are stronger than electromagnetic interactions. So for this reason, protons are still sitting in the same nuclei, not are expelled due to electromagnetic interactions. And as I said, Yukawa introduced the theory with a mediator, and that was Yukawa particle, which we call now fine. This is massive particle, and therefore the potential, or the potential which produces forces between protons and neutrons. So and here's the N. And also there are charge fines, not only zero you have, but also charge fines when proton changes by to neutron. The potential as a function of distance is given by this. So that would be Yukawa potential. But because of finite mass of the mediator, the potential exponentially cuts here at radius which is inversely proportional to the mass of the fine. So this is the form of the potential for strong interactions. So it has small radius which is inversely proportional to the mass of the fine according to Yukawa theory. Now of course we know much more. So we know what is behind this picture. And this is not complete of course picture. So now we know the strong interactions are mediated by gluons, which we discussed it. So fine is also important. It is important because actually we have phi 0, phi plus, and phi minus. Discovered actually 3 particles. And so these particles are important for classifications of hadrons. Which eventually led to introduction of quarks. And also fine is very important source of neutrinos. As we will discuss. So, now fine has been discovered by Bristol group in UK. In 1947, and the group led by Lattice, Occhialini, and Powell. The source of fines was again cosmic rays. So this is source for without any cost. So these particles arrive from the space. The detector was photographic emulsions. So let me explain how this method of the detection works. And the idea again is to see the tracks of the particles and visualize the tracks of the particles. And what emulsions allow to do this. And this technique is also used presently in various experiments. So the emulsion technique allows to visualize the primary effects of the charged particles, namely ionization. So these techniques and this one of the first experiments uses so-called silver bromide. So these are molecules of silver and bromide. This material is transparent for light. The way we see tracks in this material is the following. There are three steps. The first, ionization. So charged particle enters your emulsion and produces ionization. It ionizes molecules of silver bromide. Second point is development of emulsion. So this is some chemical procedure which actually leads to appearance of free atoms of silver. So it gives free atoms of silver. It destroys molecules, ionized molecules. So molecules are ionized and the chemical procedure leads to the destruction of molecules and appearance of atoms of silver. Then, when these atoms appear, what they do, they cluster. So clustering of argon atoms and formation of grains. Of this argon. So these grains contain many atoms. This is kind of empirical. It's not like people plan this, just due to developments even in some other areas. It was established that when you have these atoms of argon, energetically more profitable if they form the grains. So the potential energy of the system decreases when these atoms are not separately but form some grains. These grains are not transparent to the light. And therefore you can see them if they grow big enough. So this is what we see actually. We see these grains of silver, right here, the silver side. We see the grains of silver which are formed after ionization of these molecules. Now what were the observations? The Bristol group has observed various events, and in particular the events of the type which are kind of interesting and peculiar. So let me draw this and then we will discuss. And I will show you then, I think I will just probably send you the slides with all these pictures. So what they see inside the emulsions were the following. Tracks of this type. And these are classical kind of pictures which you can find, I think, in any particle physics book. So they see these funny tracks with three parts. And the properties of these tracks are the following. So there are three tracks. Let me name this 1, 2, and 3. The track 1 becomes thicker, which is actually indication of ionization energy loss. And then at this point, probably there is some decay. The first. Track 2 also becomes thicker, and what is amazing, that the length, and this is crucial, of this second track was practically the same in all events. And the track 3 is thinner, and even becomes more thinner when you go out of this production form. And this is indication that we deal here with radiation energy loss, right? What is also clear, that in both vertices, there is visible E and P missing. But clearly you cannot satisfy energy momentum conservation once you have just this particle and it produces something, and that's some kind of. Now suppose you are experimentalist like this group. Well, how you would interpret this? So this is what they knew. This is all information. And now you need to give interpretation of these events. Let me give you one hint. Well, clearly, at that time it was almost immediate conclusion that here probably neutrinos are emitted. And there is some decay of particle, and neutrino is emitted. And so you do not see, so neutrinos take energy and momentum. And also here, neutrinos are emitted. What else you can say? Actually, the information I give you in the previous lectures, and especially information about energy loss, is enough to make complete description and interpretation of this event. Any idea? And again, one of the crucial things is the same size of the second track. Any guess? Any kind of idea how we can produce this? Which track? So we have 3. So what? 2. Yes? What? So what do you want to say?
It could be the muon particle.
Yeah, so what experimentalists did, they started to try. So can it be electron, or can it be muon, can it be photon, and the same is for this, and for them the same is for that. So that's right, it turned out that these tracks are due to muons. Now, why the tracks are of the same length? It's even kind of contradicts quantum nature, right? You have decay. When we are talking about decay rate tau, or decay rate or lifetime, eventually this is quantum process, which means that these are characteristics in average. So if you have lifetime 2 × 10⁻⁻⁶ centimeters, it doesn't mean that a given muon has precisely this lifetime. So it may be 10⁻⁶, it may be 5 × 10⁶, it may be 10⁸, and even more, 10⁻⁸ or even more. So our characteristics are average. How come that all they are of the same size? Well, it's interesting exercise to guess, and then you will better understand what are really problems people solve. You know, when you are reading the textbooks, everything is already clear. But even some small step, when you will write this, oh, of course it's clear, that should be like this. But it takes time and it takes efforts to actually understand what's going on. So let me describe what is really interpretation. Again, experimentalists tried first with known particles. Can it be, say, muon? Then this is what is electron, then it doesn't work, you cannot explode. So what neutron doesn't show the track. Can it be proton is stable. And so the only one they can suggest that track 1 is due to some new particle. Which we now call phi. So what happens here? The pion enters, loses the energy by ionization, stops here, and decay. So pi loses energy, stops, and decay. And for this lifetime of pion should be bigger than time of energy loss. So it should first lose energy, stop, and then decay. You can ask why. And this is needed to explain this feature that these tracks are the same for all the events. So this is crucial, that we have decay of stopped pion. Second, and again, experimentalists kind of checked various possibilities. It was kind of scanning of all possibilities before they came to this conclusion. It's not just immediate. You cannot just immediately derive these things. Now, pion undergo two-body decay. So pion decays into muon and neutrino. What does it give for us? That gives that the energy that leads to the conclusion that the energy of muon is the same in all events. Initial energy. And this is just determined by kinematics of pion decay. We have muon and neutrino, and just from energy momentum conservation and knowing the mass of pion, you can find what should be the energy of muon. For two-body decay, energy momentum conservation determines the properties of final particles completely. So this means that initial energy of muons is the same. Next step, muon loses the energy and decays. And it decays, as we already discussed, into electron and to neutrino. So actually, in this vertex, a single neutrino is emitted, and here we have two neutrinos, as we discussed before. So that explains missing energy and missing momentum. Of course, the question is still, although the energies of muon are the same in all these events, why the tracks are of the same length, since it's quantum process, right? So it may happen that in one case muon decays very fast and another slower. So the point is that again, a lifetime of muon is bigger or much bigger than time of energy loss. So that muon first stops and then decays. So it loses the energy by ionization. And loss of the energy of by ionization is multiple process. So muon interacts with many atoms before it loses the energy. And in each of collisions it loses small amount of energy. And when you have this multiple process, it almost becomes classical, right? If you have just single event, or single decay in space, or just one interaction, then it's clearly quantum nature you see immediately. But when you have thousands and thousands of collisions, many collisions, you essentially come to kind of averaging situation. And therefore, this process is almost like a classical. And therefore, the length of trajectory is determined by initial energy. And that explains equalities of lengths of tracks in all these events. Question?
Yeah, one question. At this time, this was proposed only for a decay in this way, but how about other possibilities? How do you exclude other types?
Well, first tell me what is other possibility. Again, you can say, okay, maybe this is muon. So maybe this is muon. We know we knew this particle, right? But then what will happen? Then this should be electron, right? And then how you explain this feature? It cannot be neutron, because neutron is neutral. It doesn't produce any ionization, or at least it is clearly charged by it. It cannot be proton. Proton doesn't decay. So that time, number of particles was too little. And then immediately comes, so that should be some new particle. And let's try to explain this by known particles. So this is an easy situation. You can really, in 10 minutes, check all other possibilities. Nowadays it's much more complicated. When you see events, you may have, 10, 20 different interpretations. And then you need to select correct one. And very often you need even to have some additional experiments to select among possible explanations. Okay? More questions? So now let us construct the theory of ion decay. Let me remind that we deal here with ion, which is transformed to muon, and neutrino, a single neutrino. Well, one thing is kind of clear immediately. We have again appearance of so-called lepton pair. Similar to what we have in the case of muon decay. Now, how we can write the Hamiltonian, which is responsible for this decay? What you would write? How you would write the Hamiltonian? Any idea? So again, you are a theoretician. Now you are a theoretician. Now, tell me how you would describe this. which kind of Hamiltonian you would write. Again, using analogy, you can try the following. You can write this as some G coupling constant, let me put here 5, square root of 2, as a product of two currents. Again, this is straightforward. You see, there is a kind of deep sense. This is kind of a unity of nature. So nature repeats the same things in many places. So it's not so stupid to start with some analogy and try the same which you learned already before. You can say, okay, maybe this is the product of two currents. And so one current is leptonic, and similar to what we had already in muon decay. And this is something else, some another current, H, plus Hermitian conjugate. And one is simple, as this leptonic current, which is mu. Now let me write it again, as I did already before, 1 minus gamma 5 and mu. This current would actually describe production of muon and neutrino. So if it is pi plus, then it should be mu plus. So mu plus is produced here. That would be from, so let me put here minus, and then it will be the same current. Minus, a muon is produced, and here is antineutrino. And this is precisely what this current describes. So it describes production of muon. And this is production of antineutrino. It describes annihilation of neutrino or production of antineutrino. Okay? So, this is leptonic current. And this is hadronic current. And what is this hadronic current? I put here mu index, then I should put index here, mu. And here it's up. So that let me put it mu here, and this is hadronic current. So we don't know what is this, what we can write. Don't even know that this is vector current. Let's take vector current. We don't know what it is. Actually, it may happen that is not described by current, but just something without gamma mu. But let us assume that here we deal with the same type of the interactions, which are interactions of currents, and therefore we have gamma mu, and therefore things which are describing fine, its behavior, is also described by some current, because we want to have Lorentz invariance. Therefore, we need to have something with index mu. So what is interesting, even not knowing explicitly what is this current, hadronic current, we can do a lot and we can proceed with computations quite far. So let me do this. What you should compute, you should compute matrix element with between final state mu and neutrino, Hamiltonian. So I have it from 5, let me put it 5. And here is fine. So inserting expression for my Hamiltonian, I can write this as G fine square root of 2. This is some constant, I can put it out. And then since Hamiltonian factorizes, it's a product of two currents, I can factorize my matrix element in the following way. So, hadronic part. In final state, I have no pi. I have no any other particles apart from two leptons. So I put here 0, and I put here this current, and initial state is fine. Then I have muon and neutrino, and here I put leptonic current. And this is 0. So, in initial state I have no leptons, right? So leptonic part is just like an empty. And in final state I have muon and neutrino, and this current should produce from vacuum this muon, neutrino, and muon. So this part describes disappearance of pi, so we have pi here, and there is nothing in final state. So this current should describe disappearance of pi. Agree? Well, this is important trick that may be useful for any other pure considerations. So what we can say about this matrix element? This matrix element has index mu. And when we compute it, and remember eventually all the computations, all the results of computations eventually lead to something which is expressed in terms of momenta or spins or things which we observe, right? So the only vector here, core vector, which we have in the problem, is the momentum of pi. So even not knowing anything here, just from Lorentz covariance, since here we have 4 vector, then on the right hand side it should be 4 vector, right? And therefore, the only what I can write is momentum for momentum of pi. Now again, I can use the arguments of dimension, and it turns out that this has dimension mass to the cube. Remember, we did this estimation, this appearing. And these are wave functions, so to say. And each of these wave functions has dimension square root of m. So we will have here m cube, which comes from this, and then m square from square root of square of due to pi and 0. And therefore, what we should have here should have dimension of mass square. Right? So this has dimension mass square. And therefore we need to add something here which has dimension of mass to match dimensions. So it's already not small, right? So just without knowing anything here, we can conclude that our matrix element should be equal to momentum of pi and some constant, which is actually called fine decay constant. Which actually has very deep meaning. And eventually, let me just take, say this term, and just you appreciate that this is really very something very important. So this is nothing but vacuum expectation delta which breaks chiral symmetry. So in the 60s, this kind of theory has been constructed. So eventually what happens is that this coupling constant has very important meaning, as a physical meaning. Okay. So if someone will work on this chiral symmetry, this is what you will learn in the first place. By the way, the size of this coupling is close to the mass of the prime. It's 130 MeVs. That has been measured. And that also makes some important sense, close to the mass of the prime. But anyway, once we made this estimation of our matrix element, we can further proceed with computations of the amplitude. Did what I have deleted. So let me continue. The amplitude is GF, so it's G pi square root of 2 F pi. And now what I will use energy momentum conservation, and therefore this momentum of prime, I don't want to confuse because I use the same index, is equal to momentum of muon plus momentum of neutrino. Just we have two-body decay and energy momentum conservation, and this allows me to express this fine momentum as a sum of muon momentum and neutrino momentum. So I will write here P mu plus P mu, and I have U muon, gamma muon, 1 minus gamma phi, mu muon. So now I put here Smirnovs, right? So I have this muon and nu, but that was abbreviation, right? Eventually what I mean by when I have written Hamiltonian are the wave functions. And when we do computations, we have operators first, but then when we do connections, what is left is 4 spinors, which correspond to muon, and 4 spinor, which corresponds to neutrino. Okay, ask me questions. So what has been written before? It was mu, gamma mu, 1 minus gamma phi, mu. But these are fields, so these are operators. And when I compute the matrix element, so I make connection. So here I have a 0, and here I have mu. So I make connections of this type, and so using anti-commutation relations, and then what is left out of this computation is this expression. So what is left? 4 spinor of muon and 4 spinor of neutrino. Okay? I think you will learn this much more, you understand this much more, but this is quite simple because here in these fields, they always have, when we are doing expansion in the second quantization, we express this in terms of wave functions and operators. So that's what is left out of the wave function. Okay? Now, next step. And remember this trick. Please remember this trick. It may be very useful. So we have two terms. One is with momentum of neutrino, and another is with momentum of muon. So let us consider them separately. Neutrino term, what I have here, U mu, gamma mu, and I put here P mu, here's 1 minus gamma phi, and here is U mu. Right, so I just take this term, I put this P attach this to mu. So what is this? This is nothing but P mu of neutrino. So I can actually permute and write as P neutrino, and here is spinor of neutrino. And due to Dirac equation, that will be mass of neutrino and again the spinor. And mass of neutrino is extremely small, so I can neglect this. Okay? So this is the result from this momentum. And I can repeat the same things with this P mu. And what I will get is U mu conjugate. And then it will be P slash mu 1 minus gamma phi and U mu. Tell me if if something is not clear. So I have this, and I connect with this gamma matrix. I have this momentum slash, and now again I can use the Dirac equation, and U mu P slash equals U mu multiplied by the mass of the mu. Okay? So, let me then conclude with this amplitude. It will be G phi square root of 2 F phi, and then it will be mass of the muon, and we have here U mu 1 minus gamma phi U mu. Okay? So, we know everything up to this F phi. And now we can compute what is the rate. Right, what is the rate? So we need to compute moduli square of this expression and sum over spinorial indices. And what I will get clearly, I will get G phi square when I square this. I will get mass of the muon square multiplied by F phi square. And now what is left out of this square, as again can be reconstructed immediately using dimensional arguments if you want. But it is clear that it should be something which has dimension mass. And in the first place, what I should write is the mass of the fine. It's clear if mass of the fine is 0, then it should be 0 decay rate, because massless particle cannot decay. Now let me write precise expression. So that's immediately then drawn. So this is exact expression, G phi squared over A phi. Here we have two body decay, and therefore amount of phi, or power of phi is smaller by phi squared. F phi squared and mu squared m phi. And here is the following factor, and then I will explain the origin of this factor. It's m mu squared over m phi squared, and everything should be squared. So, if mass of the muon is very small, then this is just 1. So this factor appears because the energy release is not the mass of the fine, and when we do integration over momenta of the particles, of course the free momenta are when we subtract m phi minus m mu, because this is not available, right, for our momenta of final particles. So, also if muon mass approaches the mass of the fine, it should be zero, right? Because decay cannot occur if the mass of this particle equals the mass of this one. So this type of the expression appearance is quite clear. Now we discussed mode of decay of fine into muon and neutrino, but there is another decay mode into electron. So fine can decay into electron and neutrino. So what you would write for this decay rate? So here, of course, the mass of the electron is much smaller than the mass of the fine, and naively you would expect that this decay rate should be bigger than decay rate with emission of muon. Again, remember that the mass of the muon is 105 MeVs and the mass of fine is 140 MeVs. So they are close, and therefore this factor is substantial. But for electron, it's very light, you can even neglect. So, what is the rate of this decay, gamma E? Is it bigger than gamma mu or not? Oh, yeah, gamma mu. Any guess? You understand what I'm saying? Usually the bigger the phase volume or kind of bigger possibility for final particles, momenta, the bigger the probability. We always are doing integration over momenta of final particles. Here we have more momentum. So for instance, momentum of, so that's just more free stuff. So if you just take this factor, then it will be electron you can neglect, and there is no such a suppression. Any guess? So what is this ratio of rates with electron in final state and with muon in final state? So, okay, you see this factor. It turns out that the rate is proportional to the mass of charged lepton, which appears in this decay squared. So, for electron, I need to put here mass of the electron. So then the first approximation, this should be proportional of mass of electron over the mass of the muon squared. And this is 5 orders of magnitude, so that is 10 to the minus 5. Which means that in spite of the fact that the electron is much lighter than muon, this decay is strongly suppressed. It is suppressed by the ratio of masses of electron and muon squared. And therefore, fine decays, this is important, extremely important for searches of oscillations, for instance, which we are doing now. that the pine is mostly source of muon and muon neutrino, and not a lifetime neutrino. So actually this fact, we derive this. Remember how it appeared, because we have a hadronic matrix element which is proportional to momentum, for momentum of charge left. And then we used Dirac equation, and that led to appearance of the masses. Actually, this result can be obtained by just considering the angular momentum conservation. When we have pine, which has spin 0, so this is pine. So initial state has angular momentum 0, and then you have in the final state muon and muon antineutrino, or electron and electron antineutrino. And then I will not discuss, probably I will give you as an exercise with some additional information. Just making this consideration, and from the condition that total spin in the final state should be also 0, what is important that you need to take into account correct helicity of this particle, and therefore that leads to appearance of this mass of left. So you will check this. Now let me make summary of what we learned and what are important consequences of discovering pine. Lifetime of pine has been measured, and it was found that this is 2.6 10 to the minus 8 seconds, which is precisely what you need for U-colored pine. That was estimation actually. So pine is U-colored pine. The mass of the pine, as I said already, is approximately 140 MeVs, which is much smaller than the mass of the proton, and pine is much smaller than the mass of the proton and some other particles. So pine is strongly interacting particle, and it turns out that pine is the lightest, and it is substantially lighter than other strongly interacting particles. Theory has been developed which explains this fact, and symmetry, specific symmetry, let me just mention this. I don't want to develop this, and I don't want to ask you then that you know this result, but eventually someone of you may work on similar subject. So it was introduced so-called chiral symmetry. Related to the fact that H fermion can be represented as left plus right component. And left component is 1 minus gamma 5 over 2F, and this is 1 plus gamma 5 over 2F. We always can write this, and this is what is called left component, and this is called what is right component. And it turned out that Lagrangian of interactions, strong interactions, is actually invariant with respect to rotations of left and right components independently. This is what is called chiral symmetry. And so what happened is that chiral symmetry is spontaneously open. That's what happens also in the standard model. And when this happens, that some particles become massless. And so in the first approximation, pions have 0 mass because of this spontaneous breaking of chiral symmetry. You can hear these words or some read somewhere. Again, I'm not requiring you to remember or understand this. I'm just, some of you may know. Actually, this coupling constant, S phi, which we have introduced, is nothing but vacuum expectation value which breaks this chiral symmetry. So pines are massless in the first approximation, and they acquire masses due to explicit breaking of chiral symmetry because of quarks have masses. You see, what is the big rich physics is behind all these things. And in fact, Weinberg was working on this chiral symmetry and pines, and actually he also developed this formalism of spontaneous breaking of chiral symmetry. And then later, he decided to apply this spontaneous symmetry breaking to the standard model, what we call now the standard model. In the standard model also there are this phenomenon of spontaneous symmetry breaking. So pines, let me write this and I will not develop more, are so-called Goldstone bosons. And Goldstone developed the theory, if there is spontaneous symmetry breaking, then massless particles appear, so Goldstone bosons. So pines are Goldstone bosons of chiral symmetry. So it is not accidental that there is a relation of F pi, mass of the pine, because this is what is responsible for this spontaneous symmetry breaking. Now, the mass of the pine, it appears because of explicit symmetry breaking. And coupling constant Ga, remember, for axial current which appears in our theory. So there's a kind of theorem or relation, Goldberger-Trimon relation, which actually connects these parameters. I'm saying this just because from a simple fact, the discovery of pine, there are many things and many developments in the theory. But we will not, of course, discuss this more, what is important for us, for these parameters and the theory of pine decay, which we have considered. Any questions?
I have a question. So when you're considering the Hamiltonian term for the pion decay into lepton pairs, you consider something like current interaction. But why didn't you consider something like the QED interaction term, like K and G?
So let me try to first understand precisely. So we know that we have pion, we have neon, and we have neutrino. And therefore we need to construct Hamiltonian which contains the fields of these particles, right? That's important. Now, what is your suggestion like in QED or what QCD? What's yours? Say again.
Something like A mu, G mu, some field which is related to the
A mu
and
what?
And J mu lepton.
What is J mu?
A mu is related to pion field and some other J mu which is related to lepton.
Okay, so let me put it. I don't know how to talk about J mu. This is what you want to say?
Yes, I mean J mu lepton. I mean the lepton current.
Current, right? J mu. Something like this.
Yes.
Okay, so the point is that here, if you want to introduce elementary field, it cannot describe pion because pion has spin 0. That would be some vector field, a vector boson, to spin 1. why we are not using this. Eventually you will see that this current, we will consider this, we will come back to this. This hadronic current can be explicitly written in terms of quarks. And it has very clear and simple structure in terms of quarks. When we will come to the quark structure. So this is clear because we need to describe this pair. And now for this elementary vector field doesn't work, so it's a scalar field. And therefore what we are writing here eventually is reduced to momentum, not to the field, but the momentum of pi to have Lorentz covariance. Thank you. Okay. So then we stop at this point.